There's no angle for the zero vector. So the zero. Yeah, like there's a notion of orthogonality where the inner product is zero. Yeah. No, the issue is that there's no notion of angle with the zero. I think she meant to write non-zero vectors. So that's all.
How do you know that? I know for a fact zero. But wait, you mean here or in the answer? Like this just has two vectors. But the zero is perpendicular to zero, and the angle between 0 and 0 isn't 90. So what is this equal? It's just I'm not a but is whatever. And for the if and only if the and orthogonal, I think it's for non-zero. Okay, that one. Yeah. But for perpendicular, it's similar to parallel. It's a geometric point of view. So what I think in other words, C has a matrix. What I'm saying is that we have to choose that this is what is C? One thing what if this one is zero? Oh no, I see that. No, I like this. Yeah, so you want to do it by what is P? P is P of I, and P you want the P not I. Let's see again. Why do you make it close? So it becomes
Because you have some. Yeah. Yeah, why not? Identity minus one. Then another okay, let me just start. Yeah, as I said in the beginning, this is not only for agriculture. We have Cesar, I didn't see any questions. So make sure you're comfortable up to Agile that we can do today. And yeah, that's it. Okay. Okay, so this week we can approve all our spectral theorems. 30 slides. Let's see. Well, I mean, I've done a little bit last week, so you know. Right, so last time we talked about that for any linear map, you have an upper triangular representation. Okay, so spectral theorem says that if you have some conditions, you're diagonal, but it turns out, yeah, when you're over the complex numbers, so like we talked last time, you can always do upper triangle. And going back to 2 to 3, this is because you can do Gaussian row eliminations and reduce it to row echelon. We call this row echelon. Okay, this was called row echelon. So that's all is happening here, nothing more. And you can do this for any matrix, so you can do it for any linear map by the one-to-one correspondence, also proved in your homework problem. All right. When your underlying field are the reals, this is no longer true. So this matrix here, you cannot write it in this form when the entries are all real. But at the very last slide, I will do this for complex. So I can do this for complex, but I cannot do it for real. Okay, so the very last slide gives this for complex. All right. Yeah. So spectral theorem says you can write as diagonal. Jordan form theorem says that for any map, again, not only you have upper triangular, you have almost diagonal. So it would be eigenvalues, and then above the diagonal, so it would be something like, 1, 2, 3, 0, and then like a 1 or 4, and then 0. So like just above the diagonal, you have stuff, everywhere else is 0. That's called Jordan block matrix, and we will prove this for all matrices. Wait, what happened? No, it's like just above the diagonal. How do I make it bigger? Let me put more entries. So, you see, above the diagonal. So, 4, 5, 6, and then 0, 0, 0, 0, 0. Okay? Then, right, then you learn to do this using Gaussian row elimination. So last time we did this example, which is not diagonalizable. So we found the eigenvectors, found eigenvalues, and we got multiplicity 2. So this is algebraic. This is geometric. So geometric is 1, which is not algebraic. So using our criterion, yeah, M is not analyzed. However, even this guy has an upper triangular matrix representation. So it's not diagonal, but you can still write it in upper triangular. And that's what we're going to prove, right? So the statement is any matrix can be written as stuff, the eigenvalues, stuff, and 0. I mean, any matrix over the complex numbers. Yeah, and we talked last time that you can find these P matrices explicitly using Gaussian row eliminations. These are called the elementary matrices. So you talked about this. So you can find these matrices explicitly, and there's a big business in linear algebra of finding the fastest way to get P matrix. And there's so many algorithms out there because that's really what people care about. All right, so we're going to prove that any matrix can be written in upper triangular form if you allow me to use complex numbers for the P matrices. Okay, so let's do that. So we said we do this by induction, dimension equal to 1. We said that this is just a scalar, right? So it's immediate. The matrix is just one entry, so it's upper triangular. So suppose you have this for all subspaces of V with dimension strictly less than V. Okay, so that's our induction hypothesis. We're doing induction. This is the base case. Okay, and now we have to prove that T is upper triangular. So T beta is upper triangular over V. All right, let's do it. Yes. An easy condition for upper triangular is the following. It means that there's a basis for U so that you have the following condition. So let me remind what this means. Now let's do it again. So let's explain the condition TUI in the span of U1 to UI for all I1 to K. All right, so remember T beta are the columns of TU1, TU2, and so on, right? This is the guy. And what does it say? It says TU1 is equal to some combination of U1, right? This guy over here. That's what it says, because you go up to I. So TU1, you put lambda 1 and then zeros. TU2 is equal to, let me put AI actually. So this is A11U1. TU2 is A12U1 and A22U2. Okay? So A12, A22, and then zeros. Right? Okay, good. So yeah, anyway, so you keep doing this and you get your upper triangular matrix. So in other words, when somebody asks you, prove me upper triangular, instead of doing this crazy stuff with matrices, just prove them this condition. That TUI is in the span of U1 to UI. Okay? So they're equivalent. Okay? All right. So this is the equivalent condition. Now let's build the subspace U, and then we're gonna augment U with some other space, and technically U curve, and we're gonna get V. So, but we have to build U. So let's do that. And but basically, this proof is called sure decomposition. So the way we're finding these bases, there's an algorithm behind it called sure decomposition. So this is a constructive proof. This is not existence. It's not an abstract. All right. Every linear map has at least one eigenvalue, and let me remind you again why. This is because the characteristic polynomial is a polynomial, and by FTA, it has at least one root. At least one root over C. And we said that roots of characteristic are eigenvalues of T. Okay, we can go back and forth. Right? Is that okay? So every map has an eigenvalue, call it lambda star, right? So I call it, what do I call it? This is lambda, okay, right. So now take U to be the image of this space. So take this to be U. And we're gonna build on this. So we're gonna apply induction hypothesis to this, and then augment to the whole space to get upper triangle. To apply our induction hypothesis, we need to show that dimension of U is strictly less than dimension of V, right? That was our induction. And so let's prove that. So by rank nullity, dimension of U, which is the image. So let me go, it's not here. Yeah, so U is this image. So rank nullity says that this plus dimension of kernel of T minus lambda I is dim V, right? This is rank nullity, right? All right. So in order to show that this is strictly less than this, what do I have to show about this? Yeah, there is at least one. And since you have an eigenvalue, how shall I say this? No, let's just do it here. So since eigenvalue exists, you get that eigenvector exists. That no. It can be complex, the lambda. Since eigenvalue exists, eigenvector exists, and so you get that the kernel. So namely, you can write TV equal lambda V for all V in the span of some V naught, right? And so you get that the kernel of T minus lambda I contains the span of V naught. And dimension is a increasing function. So, okay. No, because we just need to apply reduction hypothesis. Yeah. All right. All right. You have a question? I mean, this is the core argument, because now we apply a reduction hypothesis. So this is the main point. Do you have a question? Yeah, so how do you get this? So using our argument above, we get that. And so we can apply inductive hypothesis to U equal to image of T minus lambda I. So you can find the matrix, you can find a basis so that this guy has an upper triangular representation, call this B. So TB restricted to U is upper triangular. Or equivalently, we have this span condition. So for proofs, this is much easier to work with. When you do numerics, you want to work with matrices, but for proofs, it's easier to work with this span condition. So, okay, you have that. And now we do our usual augmentation argument. So this is a basis for U, and this is a basis for the entire space V. Right. And you can get this with Gram-Schmidt if you like. Right, our matrix. So let's do this to give you an idea. So what it says is you want to find TB. You want to find TB. And you know that for the first entry, so this is TU1 all the way to TUN. Right? Like column vectors. But you already know you have the span condition for the first K of them. So can somebody tell me how does the matrix look like up to now? Perfect. So you have TU1 or stuff 0, stuff 0 up to K columns. And then stuff. And the stuff are the TUK, T plus 1. To TUN. Okay, that's all you know so far, but you want to get the full thing. So let's do that. Okay. All right. So, right. So you want to show that the rest of them are also upper triangular. So you just take any one of them. Like let's do it for TK plus 1. And you want to show that it's in the span of the previous ones. All right. So this step I didn't do anything. I just added and subtracted. Subtracted. What is it? T lambda UKI, or no, lambda I UKI. Okay, so I just add and subtract that. And let me ask you a question. This first guy, can you tell me where does it belong? The answer is in the slide. So, I mean, kind of. Why? Yeah. Is that okay? So U is the image of T minus lambda, i.e., these are all the V's in V, such that V is T minus lambda I for some W. Yeah. So this guy is in U. Yeah. Okay. So this guy is in V. So what can you say about the summation? It's in what? U plus what? Yeah, say it. What is it? Yes. Um, I think you're, let's see. You said of T minus lambda I? I think you're right. But I mean, it's easier than it's just in the span of UK plus I. I don't know. And the question is, so, is that okay? What? What is it? Yeah. No. Okay. Maybe my question was not clear. Like my question is, where does this belong? Yeah, because of what we just said. Because this guy is in U, and this guy is in the span of UK plus I. Okay. I don't know, like what the confusion was. So, but then, uh, but then this is a subset of exactly this. So this is a subset of span of U1 to UK, and then UK plus I. So that's it. This is called upper triangular. Okay, I didn't need the other. So just to show you what that means. So you go to the TUK plus 1, and it's stuff up to up to K row, and then also the K plus 1 row, but then there's no dependence on the other stuff, so it's just zeros. So K plus 1, and then K plus 2, and these are all 0. Is that okay? So you got your upper triangle. That's it. And this is very constructive. So you can, this is called short decomposition. So you start some vector and you keep taking perpendicular subspaces to find the, to build the basis. The hard part is building the basis. All right. Okay, we're not done. So this is interesting because they're not just upper triangular, is eigenvalues of the matrix of the map. So you're almost at the spectral theorem. So how do you do this? So you take this difference and you look at its matrix. Okay, so you look at this matrix and take lambda to be an eigenvalue of t. So since lambda is an eigenvalue of t, what can you tell me about t minus lambda I? Since lambda is an eigenvalue. Just to see if you're yes. Yeah, thank you. So, right. So since the determinant is 0, you get that is non-invertible. Actually, I like it the way with kernel. Yeah. So since there is an eigenvector, you have that the kernel is non-empty. I don't know why I keep talking about injected. I mean invertible. So this is non-empty. So it's non-injective. Yeah, much easier. Okay, so what was my question here? Right, yeah, non-invertible is okay. And then what? Yes. Oh, I see. Whatever, it's been answered. So exactly, all we wanted was the determinant is zero. And I think you've already understood how this connection works. So as long as you have eigenvalue, you get determinant is zero. And so you have determinant of this, determinant of that. So this is zero. But what is the determinant on the right? Can somebody tell me? What is it equal to? Let me see if anybody else. Okay. Yeah, so it will be product of C k minus lambda from k1 to n. But it's zero. So what does that mean? Huh? What? Yeah, but since it's zero, what does that tell you about? Perfect, yeah. So there exists a C I that is equal to lambda. And that was one eigenvalue, and you keep playing this game. So namely you put lambda, and then, but they're distinct, so it will not be zero, right? So let's say you call this lambda I, since you know it's the ith one. Then you look at lambda I plus one, not lambda I. Yes, question. Then you will have ck minus lambda I plus one times lambda I plus one minus lambda I. But this is not zero, right? So that means the other C's, one of the other C's will need to be zero. Okay, yeah. Oh, no, they could be the same. It's just, yes, right. So, right. Like what will happen is in your diagonal, the CIs will be repeated. Let me see if I understand. So the concern is whether you have algebraic multiplicity, you have multiple, right? And then what I'm saying is that, I mean, I'm not assuming, let me see. What I want to say is that you would detect it here. It would be Ci to minus lambda Mi. So, right, okay, yeah. So here's a way to see this, to catch even this, right? So you can write determinant of t minus lambda I. You can write it in terms of the multiplicities. So lambda one, lambda to m1 to lambda k is strictly less than n, to lambda mk, and then you just compare the two sides, right? So this guy will be a product of the ck minus lambda, and so m1 to k, or no, n. But we already said that one of them is one of them. So you literally will be lambda 1 minus lambda. So I2 to n ci minus lambda, right? Because we already showed that at least one of them, but then they have to match by Euclidean division. Yeah, and the way to extract it properly is you equate them so that you know what you're aiming at. Otherwise, you're in the dark. You don't know what the multiplicity is. And then you do Euclidean division, and then you study the new polynomial, but then the new polynomial is also 0. And then so there is another c will have to be equal to the lambda. Okay. So you divide and you end up with I2 n ci minus lambda, lambda minus 1. And then you repeat, there will be some C3 equal to lambda. All right. Well, that's a very good question. Thank you. Okay. So, right, so you got your eigenvalues. And yeah, that was it. So we got upper triangular matrix. All right. So now we're going to go into speckle theorem. We're going to prove the stronger version first, called the real speckle theorem in axilla. And then we're going to prove complex. But in practice, people use the real one. So I wanted to put more time into it. Okay. So we need the following concept of adjoint. I mean, this was up everywhere. Because it's basically integration by parts. So the adjoint of a map is the unique map T star. I will prove existence in a second. Such that for all V and W, you can go from left to right and back. Okay, so you can move the T star to the right. You might ask, how do you know this map exists? So I'll show you in a second. So this map is called the adjoint. And the one we care about is called self-adjoint. So when T is equal to T star, we're going to prove that this is the same as being diagonalizable. That's basically the speckle theorem. I mean, that is the speckle theorem. Similar, you mean the change of basis? No, T star, like equal, like the same map, not equal. Difference between oh yeah, they're different, but they're not comparable. Yeah. Subadjoint. When your underlying field are R, these are called symmetric maps. And when they're complex, they're called Hermitian. So this is in physics. If you're in physics, you would say this. Quantum mechanics stuff. So why do we care about self-adjoint? Because we have the speckle theorem. So you give me real, actually, or complex. It's for both. Axel does it for real, but the proof works for both. And I will do it for both. So you'll see. Then you have the following. T is self-adjoint if and only F diagonalizable. Okay, very nice result. So it means that if T star is T, then you can find some basis where your matrix is diagonal. That's the speckle theorem. So read Axler, chapter 7. Because it's not in the book. How do you find the adjoint? How do you know it exists? So you're going to prove this in your homework, problem 3, I think. See, right, visual presentation. So let's chat about this result. So functionals. The most common functional is the integral functional. So let's say on continuous functions, C0, 1 to R. It's the integration, right? Take f to its integral, right? This is called a functional because it takes the vector space v into a number, right? So you start with some crazy function, space, which is uncountable, and then this functional spits out numbers. So this is the context we're talking about. This is not V to V, this is V to R. So this is not linear algebra, this is more like functional analysis. Right. And so for these maps, you have the following thing that you can find a unique representative. Hence the name representation. This is called representative T. So that you can write this formula. So TV is equal to V comma UT. So let's go back to that example. So take C01 and take T to go from V to R, or maybe integrate with something. So take F to the integral of F against the Gaussian. Yeah, 0, 1. Okay, what would be my representative? Oh, it's kind of stupid example. Who's my representative? Just to see if okay. Yes. So this is, yeah, this is the Gaussian. We take V with the L2 inner product. So I just put the thing here. I just want to see if you follow definitions. This is not, the point is, you will most likely see this, then you will see some abstract map. Representation says that's all there is. That's what, yes. The inner product is 0, 1, L2. Yeah. Yeah, the map is arbitrary. Yeah. Yeah, I mean, it has to be linear into reals, but yeah. And oh yeah, in the original presentation, yeah, that's the power of the thing. It can be like anything as long as it maps to the reals. It's insane. It's a crazy kind of, it's an amazing result with many generalizations and used in differential equations all over the place. Okay. Yeah, he will do this in homework 4, and he also gives you T star. So, I mean, he told us not to prove it because you will do it. So, let's get T star. What's this map, T star? It's basically, yeah, anyway. So you have a functional, you fix W, so fix W and V. And this is a map, right? It takes V to TVW, which is a real number, right? So it goes from V to the reals. So this representation applies. So there exists the US, so that you can write this map by Risch representation as VUS, right? This is the definition. This is Risch representation. So what would be T star? T star W. Don't complicate it. It's not. Yeah. Okay. You guys overcomplicate it. But my questions are easy. I'm not committing. Okay, so this is T star W. All right. So it exists, right? The adjoint always exists. For any map, for any T V to V, which is good to me. All right, let's play with this T star. No, it is V to V. No, this is V to R. This guy is V to V. We applied this representation to S, not to T. Oh, it's a trick one. Right. So let's play with examples. Take this map, R3 to R2, and yeah, let's find T star. So how do you find it? Well, you have to work with the definition. So you start from the left, you use the definition of adjoint. Okay, nothing new here. And right, so this is R3, so we're using the dot product. Okay. And we know what T is, so you can compute it. So this is T. And then you compute the dot product. Okay. All right, so what do you do from here? You have to move it around, shuffle them, so that you extract, so you write it in this form. It will be X, Y, Z with some stuff. And that stuff will be T star. So, yeah, so I rewrote this only because I want to extract T star. So this, I will show why this is the case, but that's why we do this. All right, and then the question is, how do you finish from here? How do you get that T star is this? This is a theory question. So you know that this is 0 for all X, Y, Z in R3. How to get that T star is equal to 2B, A, 3A. Yeah, but okay, let's prove it for people. So a quicker way to say this is just take X, Y, Z to be this number here, call it W. So then you get that W is 0, and then you have positive definite of the inner product, which is the same thing as what you said. It's the proof of what you said, that the only guy who's orthogonal to everybody is the 0 vector. Okay, so that's how you prove things with inner products. When you want to show that two things are equal, you bring everything to one side and you use this orthogonality. All right, good. So
XYZ equals to T star AB, or T star AB minus the whole.
oh yeah, the whole thing. So XYZ is equal to T star AB minus 2B A 3A. Yeah, but you don't know that. I mean, we've read, but you have to prove that. We are proving it now. Well, because this, okay, yeah, all we know is the dot product is 0. The question is prove that this guy over here is 0. Yeah, I did this. I wrote this. That's the trick. That's how you prove that the dot product that when the dot product is 0, then you get that W is 0. Yeah, but initially here, this is done for any XYZ. You see, you cannot, so how do I say? This stuff here, you have to prove them for all XYZ because this here element here is generic. So XYZ needs to be generic. Yeah. But anyways, that's how you prove things. So you prove everything, prove orthogonality for all elements in your vector space, and then use that the only vector orthogonal to everybody is only 0. All right. P star is linear too. So let's prove that. It's very easy. You start with this, and you have to use the definition. This is just definition of adjoint. Then you use the conjugate linearity of inner product, right? So lambda in the second slot gives you lambda bar. And then you invert stuff back. So you do adjoint once again. And this is conjugate linear. Right? And then you put it back together. And what did you show? You showed that for all. So let me do it for you and I can ask you. So for all V, let's do this again. You have the T star W1 lambda W2 minus T star W1 plus lambda W star W2 is 0 for all V in V. What V should I take? Okay. So what V should I take? Well, it will be 0, but for now, what vectors should I take? This guy over here. Call it Y. And then this condition here implies that Y is 0. So you get Y is 0. All right. So we proved linearity. All right, let's do it for matrices. These are more concrete. So take this matrix and find its adjoint. All right, so once again, you start from the left, you use the definition of adjoint to bring it to the left. This is dot product, you're over C2. And I just computed, so what I did here was 1I01 times ZW. This is equal to Z plus IW, Z plus IW, W. Okay? That's how I get the vector. And here we have to compute this Hermitian dot product. This is not Euclidean. So since it's Hermitian, you pick up bars. Huh? No, so just to remind you. So ZW XY is equal to ZX bar plus WY bar. This is the Hermitian dot product over Cn. Over Rn, X bar is X. Okay. All right, so that's just the definition. You rewrite it in order to get M star. So regroup them. And now you have the following vector. You have that ZW M star gets sent to ZW times this vector. So m star xy using the same proof as before will be x minus ix plus y. But we're not really happy with this because we can say more. And I think I say it here. Yeah. So we talked about this. But what is m star? So I don't know if there's any physics here that can probably tell me, but even from here, I hope you can kind of see it. So write m star as a, b, c, d, x, y, and this gets sent to x minus ix plus y. I'm not going to redo it, but if you solve this a, b, c, d thing, you will just get the following matrix. You will get that m star, it will be 1, 1, 0 minus I. So it's basically the conjugate transpose. And I'm going to prove this in the very next slide. So that for matrices, the adjoint is just this. You just take conjugate and transpose. And right, so since this is the conjugate transpose for symmetric matrices, they're self-adjoint. Okay, so m star of symmetric is m, so they're self-adjoint. So you have spectral theorem, and that's really the first spectral theorem that we ever saw in like math world, physics world. That namely any symmetric matrix can be split into a diagonal. That's the first occurrence. All right, we'll continue to. Well, that's chameleon. Yeah, I mean, if you're not sitting back, just email me and then, yeah, but if you don't hear back, because I have access to chameleon, so you can just send it to me and I will wait for it to get it. Yes. No, I mean, if we don't give it, that's a mistake. We should always specify. Uh, yeah, like it's always our mistake. So we always, if we give you the correct subspace, vector space, we always have to tell you what in your using. Unless we specifically want you to work with an abstract vector space or that space, in which case we should also tell you that. Just today. The same question is using contradiction. That means that for all numbers n, for all powers, yeah, I'm looking for